Okay, good day everyone. This will be a short video lecture on how we can use the Ellingham diagram. Okay, so to begin, for me to illustrate how useful this Ellingham diagrams are, we need to set up an example wherein we won't use the Ellingham diagram and see how the Ellingham diagram can actually give us a quality of life improvement as we would could put it. Okay, so let's look at this example right here. So this is a system wherein copper is oxidized into cupric oxide, and let's just say that this is done at 727 degrees Celsius, and this system is at equilibrium. Okay, so nasa equilibrium tayo, and if you remember, when we are at equilibrium, the working equation is delta G naught is equal to negative RT ln KQ, right? So let's just say for this system, we want to know what the eventual partial pressure of O2 is. So this one, ano yung magiging PO2 niya, okay? Partial pressure of oxygen once we have attained that equilibrium at this specific temperature, okay? So if we were not to use the Ellingham diagram, the way we usually do it, and this is was explained in the exam 2 coverage, no? Yung manual way of doing this is we want to compute for delta G such that we from delta G we can compute for KEQ, and from KEQ we compute for PO2, right? So usually ang ginagawa natin is we compute for the delta G of this equation, and the delta G of this equation is just equal to the delta G, we use Hess law, no? Delta G of the products summation minus the delta G of, sorry, minus the summation of the delta G of the reactants. Tama? So that's how we usually do it. Now, once we have found the delta G of this reaction right here, we can input that here. So let's just say na meron na tayong delta G of the reaction. No? So if you have delta G of reaction, then, and that's the standard delta G of reaction. No? Then we can compute for negative RT, and hindi ko na siya i-expound. No? Ang gagawin ko na lang is constant lang just to show you. So that's negative RT ln and KEQ. KEQ here is equal to the activity of the products, which is Cu2O raised to the power of 2 squared kasi 2 siya. Tama? But later, you'll find out na hindi na nagmamatter yun. No? So that's over activity of O2 over activity of copper raised to the power of 2. Tama? Tapos, we can further simplify this, itong KEQ term na to. We know that for condensed pure phases, no, equal lang yung activity niya to 1. So this term here becomes 1. Tapos we also know that's why I said na hindi masyado nang matter na, no, kasi kakancel lang naman siya. So 1. Then we also note na itong copper right here raised to the power of 4 pala to, sorry. This is 4 kasi 4 to, no. So that's copper is also a pure condensed phase, therefore activity is equal to 1, and this leaves us with just 1 over activity of O2. And remember kung ano siya, if if it behaves as an ideal gas, which is what we are assuming here, no, the activity of gas can just be measured by its partial pressure. Tama? So ito, pwedeng i-substitute natin with PO2 lang. So that gives us PO2. Okay. So if we rearrange that, this is known. So let me just, I don't know, delta G naught over negative RT is equal to ln 1 over PO2. Now, this is, all of these terms are known, no? Kasi na-compute na natin siya dito. R is constant and T is also given right here. So ito constant lang to. So this is just one equation and one unknown, and therefore we should be able to get itong PO2, no? So that's the manual approach, no, to solving this problem. If we were to find the partial pressure of O2, knowing that this system is in equilibrium at 727 degrees Celsius. Okay, and I believe we had several problems about this, no. So marami tayong mga problems, mga sample problems, and even sa exam lumabas nito, no, uh, sa LE2 coverage. Okay. Now let me show you how we can use Ellingham diagrams. When we use Ellingham diagrams, we don't actually need to calculate, no? And that's the beauty of diagrams, no? Kasi diagrams are a way to simplify the calculations, no? Based on what is already known. Okay. So if we were to take the same system, no? So let's just let me copy this. Kunin natin to system na to. And we solved it. So hanapin pa rin natin yung PO2 at equilibrium when the temperature is 727. But this time, instead of using itong mga equations na to, instead of calculating, we just merely use diagrams, no? And in particular, Ellingham diagram yung gagamitin natin. Okay? So lagay natin siya dito. Kita ba to? Let me just zoom in. Lagay ko na lang siya dito sa upper right para lang ma-remind tayo ano yung hinahanap natin. No? Okay? So, pero hide ko muna siya. So, let me just introduce this Ellingham diagram right here. No? So, an Ellingham diagram is actually just a delta G versus T na plot. No? So, if you look at it, ito, naka-delta G is delta G, and some Ellingham diagrams have it, and this is the more common convention, no? Naka-negative delta G naught siya. So meaning pababa yung kung habang bumababa mas nagiging more negative siya. Okay? So please remember this, no? Negative delta G tong plot na to. Tama? Kasi kaya yung plot natin starts from 0 tapos pababa negative siya. Pababa habang bumababa ka lumalaki yung number. That's because negative delta G naught tayo na plot. No? Okay? Tapos so that just means na whatever let's just say ano, no, kunwari lang ito tapos yan may makuha tayong value na kunwari ito this is 1,000, this is 1,050, therefore mga around 1,080 siguro, mga ganyan. That's at 1080, and yung 1080 and that is in kilojoules per mole, no? Pagka final answer natin, we should negate it kasi negative delta G siya. Okay? Pero mamaya na yun. Okay? So anyway, erase ko pala. So let me take you to yung mga important features nito delta G or yung Ellingham diagram natin. And I think I need some extra space, no? Okay? Para masulat ko lang. Okay? So, these are again delta G Ellingham diagrams are delta G naught, and in this particular diagram it's negative delta G naught versus temperature. Okay? Now, we remember the also common the formula for delta G that relates delta G, delta H, and delta S, the Gattas formula. We know that delta G is equal to delta H minus T delta S. Now, this is a constant, and if we this is a constant, no? Kasi kaya natin solve. This is also a constant. This is also a constant, no? So let's just assume na delta H and delta S are not functions of temperature, no? So if that's the case, then we can have constant, 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 and this is temperature. Okay. So if we look at it, we are plotting delta G versus delta T. So this is our y-axis, and ito yung x-axis natin. Then therefore, this is just like y is equal to b minus mx. Tama? So therefore, itong t na to, this is our slope. ano, sorry. Itong T, this is our X value. This is our Y. Tapos, delta S is our slope. And delta H uh, is our Y-intercept, no? Y-intercept. Okay? So, if that's the case, then it makes sense na dapat yung mga plots na makikita natin dito sa delta G versus temperature plot na to, or the Ellingham diagram should be linear in nature, no? Kasi linear yung formula niya. And that's why when you look at delta G plots or Ellingham diagrams, you'll see na puro sila mga linear plots, no? Now, you might look at a system. Let's just take a system here, no? Kukunin natin tong, kunwari itong zinc na system na to. So, you'll notice na si zinc system, actually, meron siya mga inflection points, no? So, let me, para makita siya. Itong system ito. This zinc system right here. So, meron siyang linear plot right here. Tapos, may inflection point siya. Tama? Tapos, dito, from here to here, meron ulit inflection point. And finally, from here to here, may inflection point. So, kumbaga, if you look at this closely, parang may tatlong, kumbaga, linear equations siya. So, may separate siya na y equals mx plus b dito, and y equals mx plus b dito, plus another y equals mx plus b dito. Tama? And that makes sense, no? It makes sense because actually, itong mga inflection points na to, so let me just erase na. Itong inflection points na to, this one, are actually the points wherein nagkakaroon tayo ng phase change, no? So this M right here, yung M, if you see M represents the melting point. So ibig sabihin, dito, zinc is liquid, or the metal in question, no? Is liquid. And notice how Ellingham diagrams are all metals, no? So look at this, uranium, aluminum, lithium, magnesium, calcium, silicon, titanium, or mostly metals, no? Merong semi-metals dito, or metalloids. Pero if you look at it, naka-ano siya, no? Naka-oxidation form. And later, I'll show some of the characteristics sa kanya, no? Pero anyway, look at this. Dito sa part na to, it's still liquid. M here represents melting. So after that, oh sorry, this is solid. Solid. After that, it melts. And if you look at it, if you plot down, pag ganyan, etong point actually na to, ito yung T melting ng zinc, no? So you can actually use also Ellingham diagrams to note the melting point of zinc, of all the metals that are shown here, no? So that's the melting point. Then so from solid, magiging liquid siya. So since liquid siya, kumbaga from this phase here, solid siya, naging liquid phase na siya. Obviously, mag-iiba yung parang ano niya, no, heat capacities, and therefore it makes sense na magkaiba din yung behavior ng delta G minus equals delta H minus T delta S na graph niya, no? Tama? So that's why magkaiba yung inflection point, magkaiba yung kumbaga slope ng line dito. Then after that, itong B represents boiling point. So after this, magiging gaseous na yung metal natin, no? And this gaseous metal, iba din yung magiging delta H minus T delta S niya, no? Or yung linear equation niya. So it makes sense na tatlo nga yung kumbaga lines niya, no? Okay? So, yung graphs natin is actually quite simple, okay? Because if you just look at the different graphs, kaya natin ma-determine yung delta G if delta T is given, and vice versa, no? Pwede ring delta T, T, pwede ring mahanap natin yung temperature knowing a delta G value. Okay? So, hindi na tayo magka-calculate. We will rely on this, on these, linear graphs na. Okay? So, one thing you'll notice about the equations here, no, is that it's always on a per 1 mole na O2. So it's written as a oxidation reaction. So that's number one, no. So the first characteristic that you must remember is that the delta G is written as a oxidation reaction. Okay? So ito, for example, ito, yung metal potassium natin is being oxidized to produce potassium oxide. Okay? So that's the first thing. Always oxidation yung form niya. The next thing is that it is always on a per 1 mole O2 basis. Okay? So usually kasi if you were to write, kunwari lang, if I were to write, let's just say, oxidation of Fe, no? So Fe plus, uh, sorry. Parang mas maganda kung, let's just say, ano yung common? Right, yung copper, no? So copper plus O2 yields Cu2O. Okay? So usually, ang ginagawa natin is that, um, mas gusto, pag binagbabalance tayo, ang natural tendency natin is, ginaganito, no? So that's 2 copper, tapos ito, 1 half O2. Parang, yan yung natural tendency. And in fact, sa mga ano natin examples, parang almost always, mas convenient na naka 1 half O2 siya, no? Okay? Pero again, pag Ellingham diagram, kailangan kasi naka ano siya, no? Naka per mole O2 na basis. So kailangan niyo i-convert yung equation niyo into a per mole O2 basis. So for you to convert that, then kailangan yung i-multiply to by 2, no? So, multiplying it by 2, obviously, kasi yung ma-compute natin, no, is, for example, ang ma-compute natin is, delta G is in a kilojoule per mole. So, multiply mo by 2 pa. So, if ito yung ginamit mo equation, no? So, pero if ano naman, kumbaga mag-self-correct naman to eventually, no? Pero just take note na always naka per mole O2 siya. So if the problem indicates na kunwari naka 1 half mole O2 to, tapos tinatanong sa inyo ano yung delta G of reaction for a system like this, then obviously may transformation pa kayong gagawin, no? To account for yung difference in the number of moles per equation, no? Of the equation, kumbaga. Okay? So, so yun yung second na characteristic, no, that the delta G is given in per mole O2. Okay? Now, another thing that we would also notice that etong um Ellingham diagram, no, although it is a primarily a delta G versus temperature, meron siyang tinatawag na nomographic features, no, or parang in a way nomogram ang isang ano, no, and let me write that down. Nomogram. So if you have a 2D diagram, no, usually if you have a 2D diagram like this, usually we are dealing with only two variables, no, and in this case delta G or negative delta G and temperature. So that's the two variables we are manipulating, and if we know delta G, kaya natin ma-compute si T. If we know T, kaya natin ma-compute si delta G, no. Now, what nomogram does is it expands the number of variables na kaya mong ma-compute, no, or kaya mong ma-establish, because of yung parang they take advantage of parang mga geometrical features, no. So siguro there are different kinds of nomograms, no, and one of the common nomograms na hindi ko alam po na counter nyo to, pero I think this was discussed in some textbooks in high school, no. Pero parang ang pinakasikat na naisip ko nomogram is yung Richter scale. So I just forgot how the nomogram was stated, no? Pero for something like magnitude, intensity, parang sigurado, let me just look it up na lang, no. Let me look it up. So Richter scale. Richter scale of parang ano to yung earthquakes. So the Richter scale is yung nomogram niya is you have, let me look, distance, so meron pala to. So it's distance, magnitude, and amplitude. Okay, so it's distance, magnitude, and amplitude. So parang kaya mo kunwari, alam mo yung distance, alam mo yung amplitude. Pag kinonect mo yung dalawa, malalaman mo yung magnitude. Amplitude, malalaman mo yung magnitude. Tapos similarly, kung kunwari, alam mo yung magnitude and amplitude, kunwari lang ito yung amplitude, magnitude, then if you connect those two, you will know the distance of the epicenter of the earthquake. Parang ganun. So that's perhaps I think that's the most, I don't know, pinaka kumbaga sikat na nomogram. Now our Ellingham diagrams are also nomograms, no? So besides finding delta G and T, kaya din actually niya maghanap ng PO2, CO, CO2 ratio, and the ito hindi siya ano no shown, pero there's some let me show you one. Ito ay hide ko lang. So this is another Ellingham diagram wherein 'di ba kanina PO2 and CO2 lang, pero dito this has a third line, no? And yung third line niya is itong H2H2O. Okay? So, kaya siya, ano no, and later I'll explain kung ba anong importance nitong mga different, ano na to, um, ratios na to. Pero this just means that for any system, kaya mo siyang ma-convert into an equivalent na system na. So, for example, yung oxidation na system natin, like, for example, ito, FeO or ito, zinc to zinc oxide. No? Itong zinc to zinc oxide, kaya ito ma-convert into an equivalent na carbon monoxide, carbon dioxide system. Kaya din ma-convert into an H2H2O system. No? So, depende na lang sa kumbaga kung ano yung working environment niya. Okay? So, yung nasa ano ata natin, nasa slides, naka-upload sa Ovle. Ito yung naka-upload sa Ovle, no? Ang nandito lang is si CO2 na line, which is this one, and si PO2 na line. Okay? So, the way it works is for you to find the ano no, itong corresponding na PO2, CO2 values, kailangan natin yung mga markers, no, or indicators. So if you look at this, meron siyang indicator, no, ito. May O na indicator dito. Tapos meron ding itong indicator ito, C na indicator. So if you're looking for example, partial pressure of O2, then you use this indicator as starting point. Tapos kung carbon naman yung, kung CO2 na ratio naman hinahanap mo, then you use this carbon indicator. And baka mas okay na gamitin ko yung kabila, no? Ito, kasi meron siyang H na itong marker na to. So mas madaling mag-compute. Okay? Or mas extensive tong graphs na dito. Okay? So, again, meron siyang O. This is the oxygen na indicator or marker. Ito yung H na marker, tapos meron siyang carbon na marker. So, again, this is for finding PO2. This is for finding the H2H2O ratio. Tapos, this is for finding the CO2 ratio. Okay? So, before we get ahead of ourselves, no, let me circle back dun sa sinabi ko na any system can have an equivalent na, any oxidation system can have an equivalent na, parang carbon monoxide, carbon dioxide system, or H2 hydrogen water system. Okay? So, let's take, for example, see, yung example na natin ng copper. So, we have 4 copper plus O2 yields 2Cu2O, no? So, that's our equation. Now, say for example, gusto natin na yung environment niya is, for example, ang environment is something like, nasa parang blast furnace tayo na parang coal yung ginagamit. Parang ano, no? So, since na may carbon ka, usually ang mga gases na involved is carbon monoxide, no? Carbon dioxide and carbon monoxide. So, if we want to convert this into an equivalent system, then ang gagawin natin is we use a certain sets of equation, no, para ma-convert siya. And the equation that we use for carbon dioxide is wait lang, let me is CO plus O2 yields 2CO2. Let me balance this out. So 2CO dapat to. Tama ba? So that's 2C, 2CO. That's 2 plus 2, 4. Tapos 2 times 2 is 4. Tama? Now, if you want to, parang convert the system, dapat baliktarin natin to, no? So we need to invert this para mag-cancel out tong O2 na to. So let me just invert that to. So I have, instead of carbon monoxide and O2 combining to form CO2, we have CO2 um, decomposing into CO plus O2. Tama? So let me rebalance na to. Ano yung balance nito? We have 2 and 2. So tama na ba? 2C, 4O, 4O. Okay? So that's the case. Then this cancels out. Now our system becomes 4Cu plus 2CO2 yields 2Cu2O. Now, sorry. Ano nangyari? No, sorry. 2CO2, I mean, yields 2CO plus 2Cu2O. Okay? Now, we can also, we can now, let's just say na hinahanap natin yung K equilibrium nito, no? So, K eq nito is activity and diretso ko na, no? Activity ng nasa taas, which is, activity ng products, which is 2Cu2O, which is a condensed phase. So, that's just 1 raised squared. 1 squared plus activity ng 2CO, which is our partial pressure ng PCO squared. Tapos, we also have itong 4. So, sa baba, this is our reactant side. Ano? Cu is a pure condensed phase. Therefore, 1 ulit siya. 1 to the 4. Tapos, CO2 is a gas. So, therefore, PCO2 to squared. Mga ganun. Okay? Now, if you simplify that, so, tatanggal to. We have now PCO over PCO2 raised to the power of 2 KQ. And that's why, yung makukuha natin na sagot dito, if you use the nomogram, naka CO-CO2 ratio siya, no? Okay? Tapos, also, let's reimagine this again, no? So, sabi natin na this is a system na, kunwari, nasa ano siya, no? Na parang nasa cold na environment wherein ang expected gases is carbon dioxide and carbon monoxide. Now, let's just say na, ito naman, itong system na to is in a system wherein water is involved. No? So, may steam, water vapor, and oxygen. Parang ganun. So, if that's the case, then pwede natin ma-convert ulit to from 4Cu plus O2 yields 2Cu2O. Pwede natin siya ma-convert into H, yung gamit yung HH2O, no? Na reaction. And yung reaction na gagamitin natin is yung hydrolysis ng water, no? So that's H plus O yields H2O. And if we balance this out, this is so 1O2 ko na para mas madali. So 1O2, so this becomes 2 and 4 to dapat. This becomes 4, this is 2. Diba? Now again, to cancel out the O2, babalik na rin natin itong equation na to. So this is the decomposition of H2O into O2 and H, hydrogen gas. So that's, hydrogen gas pala, no? Class, hindi siya H na ionic kasi parang high temperatures to, therefore nakagas lahat. So hydrogen gas siya, so that's, kung ganyan, then if I were to balance this out, then I need 2 here and 2 lang dito, hindi 4, no? Kasi hindi naman H plus yung gagamitin ko. Okay? So, tama ba? So, that's 2 times 2, 4. 2 times 2 is 4. Tapos, 2 times 1 is 2. And this is already 2, no? Okay? So, if we were to balance this out, then, ito magka-cancel yan. So, this gives us 4Cu plus 2H2O yields 2Cu2O plus 2H2. So again, this is we're working at very high temperatures, no? So itong H2O and H2 are all gases na, no? Okay? So if we again compute for KEQ, so this is sa ano natin, product side is 1, again pure condensed phase raised to the power of 2 plus PH2 raised to the power of 2 over, again, pure condensed phase, copper, power 4. Tapos, P, H2O to the power of 2, and we can simplify to um, itong pH2, pH2O na ratio, no? Parang ganyan. So that's why, again, yung nomogram natin is H2H2O ratio yung nandito. Alright? So, So meron tayong yung ano no, we've already discussed na si delta G is more than just our Ellingham diagrams are more than just delta G versus T na graphs. They can also find PO2 and PCOP over PCO2 or COCO2 ratio and H2H2O ratio as well because of its nomographic features, no. Okay? So let's just raise natin to lahat, no. So let's take the simplest case lang, no, kung paano natin gagamitin muna si nomograph. Before I proceed with yung problem natin kanina, no, yung the oxidation of copper in at 727. Okay? So let's let's first ano muna, no, simplest case muna. Let's just say na meron tayong system na kunwari Mg Mg magnesium, the oxidation of magnesium, no. Tapos, gusto natin malaman kung per mole of magnesium, so let's just say, for, eto no, plus 1 half O2 yields MgO. Balance naman, no? So, let's just say, ganito siya, no? So, we are asked is if ano yung delta G ng reaction na to, delta G naught ng reaction na to at let's just say 400 Kelvin, no? Degrees Celsius na lang kasi naka-degree Celsius na to. So, mas madali mag-compute. So, if we were asked, no, kung ano yung um, kumbaga delta G naught nito, then again, kaya ito ma-solve, no, using equations, pero if we have already the graphs, mas madali natin siya masasolve. So, let's just say 400 degrees Celsius siya, tapos we are to find the delta G of this reaction. And therefore, again, yung pinakaunang sinabi ko, no, na or pangalawang characteristic na nabanggit ko dito sa system na to is that para ano no, to make it more interesting, babalik ta rin ko na lang to. So let's just say ano yung Mg or ano yung magiging delta G of reaction of this delta G of this reaction of MgO decomposing into Mg plus 1 half O2. Okay? So, kunwari, ganyan, no? So, that's a reduction process. Ano yung magiging delta G naught niya? Okay? So, to solve this, ang kailangan natin is, di ba, um, we note that first of all, if you look at the delta G, the reactions that are noted dito sa Ellingham diagrams, again naka-oxidation reactions, ano. So whatever value na nakuha natin dito, we should be negated because this is in a reduction reaction. So pangalawa, naka 1 half O2 din to, no? So, and again, yung second characteristic na binanggit ko kanina is that si O2, itong ano natin, mga oxidation reaction is on a per mole O2 basis. Okay? So, to find delta G of reaction, so kailangan natin balikan rin to. So, if we were to rearrange ito, so, yan. Delta G, ito yung hinahanap natin, delta G of this reaction. So mangyayari is, this will become Mg, 2Mg plus O2 yields 2MgO. And ito yung hinahanap kasi natin, this becomes negative 2 times delta G naught. Okay? Alright? So, ito yung iano natin. So, whatever value na makuha natin sa delta G, i-divide natin by negative 2 para makuha yung value ng reaction na to. Okay? Kasi, ang makukuha natin from here is actually negative 2 delta G naught, whatever delta G naught this is. Alright? So, if we, look at it, Ito yung simplest na use case ng Ellingham diagram. 400 degrees Celsius and mg, hanapin natin si mgmo, which is this one. Dito lang siya. So we just use ito 400 straight up, pag ganyan, where it touches the line, then go to the left, tapos nandito ka. So the value here, again, same to sa pinakita ko kanina din, no? Naka-negative delta G. Dito naman naka-delta G siya. Delta G siya, pero lahat ng values na labeled as negative values. So this is actually just the same as if I show the other one. No? If I show the other one, kumbaga, itong kabilang naka-positive lang lahat, pero it is labeled as negative delta G naught. So technically, ito, mga negative values yan. Okay? So, just don't be confused, no? So, kailangan lang vigilant kayo. So, pero in most cases naman, ito namang mga, no? Just remember na for Ellingham diagrams and for most metals, yung oxidation reaction is has a negative delta G value naman in parang in most relevant na temperature ranges, no, negative siya, so always negative dapat to. Okay, so except for very special cases, no, and at the top of my head wala akong maisip ng very special case, no, pero in any case, or yung usual na values na, it should be negative, no. Okay, so just remember that. Okay, so if nandito siya, so for this one, so at 400 degrees Celsius at equilibrium, we are to expect that the delta G naught should be equal to this value right here. So this is negative 100. So somewhere in the middle is negative, again, pababa to, no? So negative 1050 to. So this is around, what would you say? 1080, 1075. Baka mga ganun, no? 1075, or should say 1075. So that is negative 1075. So negative 1075 kilojoules per mole. So yun yung nakuha natin. So negative 2 delta G, negative 1075, negative 1075 kilojoules per mole. And this is kilojoules per mole as written this way. Okay? So always remember na ang ang mga delta G values is, kumbaga, when you are finding for delta G values, it's always on a as written basis now, if I could call it that. So as written this way, ito yung delta G value niya, negative 1075. Pero ang hinahanap ng problem is, what is the delta G if it is written this way? So kaya natin siya i-divide by negative 2 delta G. Tama? Negative 2, I mean. So to find delta G as written this way, to find this delta G right here, ito, kailangan natin siyang i-divide by negative 2. And whatever we have there should be the delta G as written this way. Okay? So that's the simplest case, no? So, parang instead of doing all the calculations, no, parang sobrang mas madalingan naman ang buhay pag gumamit tayo ng Ellingham, no, because it's a graphical approach. It should, and this is true for most cases no, in engineering. Whenever you are given a graph instead of calculations, parang sobrang mapapadali talaga yung parang workflow nyo, no. Okay, so we have delta G, and pwede rin baliktad, no? So let's take another example. Kunwari titanium oxide. Titanium oxide, let me get a good value, 700 na lang. So we have titanium oxide. So let's simplify this. Meron daw tayong titanium, the reduction of titanium, the oxidation of titanium, O2, and let's just say na ang delta G daw na na-compute dito at equilibrium is equal to negative 700. So, kunwari, yan yung problem, no? Delta G is equal to negative 700. Ano yung temperature ng system na to? Okay? So, what is the temperature? So, ito, madali lang din, no? So, we have negative delta G. Hanapin mo natin si TI line. And TI line is this one. So, this is itong line na to. Okay? So, sabi sa we have negative 700 kilojoules per mole and it is written this way. Same na siya. Nakasulat siya the same way. Therefore, kung whatever delta G dyan, yun yung system talaga natin. Okay? So, it's always as written. No? So, we have Ti plus O2 is equal to TiO2. Therefore, kung i-solve natin to, this is negative 700. We draw a line papunta sa itong Ti, the oxidation of Ti na line, no? And then we drop it down. So, we have somewhere around, this is 900. So, no, sorry. This is 1,000. Therefore, ito 900. So, what you did say, mga 850, mga 820 siguro. 820. So, our answer will be 820 degrees Celsius siya. Okay? So, ito, that's for, ano no, finding the easy, ano no, the easy method of finding or the easy way to use Ellingham diagram. So, yun yung pinaka simplest use case niya. Finding delta G when you're given T or finding T when you're given delta G. Now, let's proceed to where we all started, no? Yung initial problem natin, which is ito yung nandito. Nasabi natin, paano natin mahanap yung PO2 ratio given uh, the temperature. Okay? So, again, usually ang ginagawa dito is nagko-compute tayo, no? So, we have all these computations before we can arrive at the PO2 value, no? Pero, using Ellingham diagram, graphical yung magiging approach natin. So, let's bring that back, no? Ito. And pwede sigurong palak. Oh, lakyan ko to. Lipat ko siya dito. Okay? And increase my size. So, again, ang problem natin is, meron daw tayo um, the oxidation of copper. Tapos, as written this way, no? Oxidation of copper. As written this way. Tapos, pinapahanap sa atin yung partial pressure ni O2. Okay? So, again, ang gagawin natin is graphical approach. So, no need to do calculation. So, in this case, we find the line. So, that's the first step. No? Hanapin muna natin line. So, ito yung line na yun. Tapos, we find the temperature, which is 727. So, 727 is mga dito, no? No, sorry, 727. This is 600, 700, somewhere dito siguro. Kung 750 to. So, somewhere dyan. 727. So, let's bring it up. 727 hanggang sa copper line, no? So, let's just say ito. Yan. Now, gagamitin natin is yung indicator natin, no? Or marker natin, no? For oxygen. Kasi hinahanap natin is PO2. So, since PO2 yung hinahanap natin, then we can use this marker. Now, we draw a line. So, kuha tayo ng line. Allow it to pass through the, where the temperature 727 touches the Cu plus O2 line. So, ganyan. Tapos, follow through natin siya hanggang tumama siya sa PO2 line, no? So, let's just say ganyan. Okay? Hope, pangit yung line. Let me baguhin ko yung colors. And choose ko lang yung 5. Oh, konti pa. Let's do 10. Okay, ulitin natin. So that's from this line, this point. Daan tayo dun sa intersection. Tapos, follow through natin hanggang dulo. Okay? Parang lit pa rin. Bakit ang faint, no? Ulit. 20 na lang. Okay? And, yeah. Weird. Hindi pala dito. Sorry, sorry. Ulitin ko. Yun. So, I should have done 5. Wait, sige. Ulit natin. So, again, dadaan siya sa, ano, yan. Pasok ka dyan. So, yeah. So, where does it touch the, saan natin? Hanapin natin si PO2. PO2 is, ito na. This is the PO2 line right here. Itong line na to. Tama? This is the PO2 line. So, if I were to draw it, ito siya. Kasi ito yung H2O, itong nasa middle. H2, H2O. Tapos yung pinaka left side, inner, is the PCO and CO2. Okay? So, this is the intersection. Ito sa PO2 line. So, therefore, ito. Now, the thing you need to realize dito sa ano, no, sa nomogram na to, and this is one of the things you must look out for is that yung yung scale dito is logarithmic, no? So if you were to find this, so the easiest way to do this is 10 raised to the power of something siya, no? So and that something is you can, since logarithmic to, itong nasa exponent, the trick is you just treat the exponent as if linear sila, no? So ganun nyo tinitingnan ang mga logarithmic line. So kumbaga, let's say for example ito 10 raised to 2 to, this is 10 raised to 4. So midway we treat the exponent as linear, so therefore ito 10 raised to 3. Tapos gitna nito is 10 raised to 2.5. This one is 10 raised to 3.5. Tapos kung gitna pa nito, then that's 10 raised to 3.25. Ganun, 3.25. Okay? So, ganun natin tinitingnan ang no, ang logarithm. You just, and ito, actually kasi diba 10 to raised to 2 to. So, this is actually 10 raised to 0. Gitna niya is 10 raised to 1. So, 10 raised to 0 is just 1. Okay? Tapos, same dito din, no, sa mga negative. So, that's 10 raised to negative 2, 10 raised to negative 4, etc. So, just treat the ito as yung exponent as linear, no? So, knowing that, tingnan natin ito. So, this is in between siya sa 10 raised to the negative 10 and 10 raised to the negative 12. And parang, sakto nasa gitna. Tama? Parang saktong gitna nata to. So, kung saktong gitna siya, then that's 10 raised to the negative 11. Therefore, ang PO2 natin, and this is already PO2, no? So, we have PO2 for the system at 727 is equal to notice na yung kanina naka 1/2 O2 pa to, no? Sas meron pa yung, kumbaga may manipulation ka pang gagawin dito, no? Para maging PO2 to. So, para mangyayari dito is kung gusto mo maging this becomes, sorry. Para ba to? Delta G maging positive delta G over RT is equal to ln of PO2, no? Tama? Tama nga ba yun? Double check ko. Sige. Kung e raised to the power of negative delta G not over RT is equal to 1 over PO2. And therefore, kung i-reverse natin yung so that's PO2 raised to the power of negative 1. Therefore, e raised to the delta G. So, positive delta. So, tama nga. RT is equal to PO2 raised to the power of 1, which is, yeah. Okay? So, tama nga yung kanina. Anyway, so, yan. para makuha mo yung PO2, no? So, kailangan mo pang i-manipulate 'to. Pero again dito, since na naka-ano na 'to, naka-scale na 'tong nomogram na 'to in such a way na pagka binago kapagka kumbaga pagka ginraft niyo siya, then automatic whatever intersection na makukuha nyo is already PO2 value. Hindi nyo na kailangan i-manipulate pa siya further, no? Therefore, ang sagot natin is PO2 should be equal to 10 raised to the power of negative 11. Okay? So, pwede rin para mas ano, no? Scientific notation tayo. 1 times 10 to the negative 11. Okay? So, um, we've solved for PO2, no? And let's just say, for example, extend natin yung problem, no? Instead of finding PO2, ang pinapahanap sa inyo is what is the CO2 ratio, or CO2 ratio, or pwede rin the partial pressure, the ratio of the partial pressure of CO and PCO2. So, using the same methodology, no? And let me use a different colored line. Pwede gamitin natin yung kung CO2 naman, and therefore gagamitin natin tong carbon marker na to. So we use this one. To. Tapos punta pa rin tayo dito sa intersection. That's the intersection of the temperature 727 with the line 4Cu, or with the oxidation reaction line. So, ganyan. Tapos hanggang dito. Okay? So, nandito siya. Okay? Ito siya. And to, estimate na lang natin, no? Kasi if you look at it, hindi na equally spaced ang ano, no? I'm looking at it, ito equally spaced, equally spaced. So, ibig sabihin yung exponent niya is linear, no? Kasi naka-logarithmic scale. So, pero apparently dito sa taas, hindi na ata masyadong logarithmic yung scale, no? Kasi this is 10 to the negative 2, 10 to the negative 4, negative 6, negative 8. Tapos hindi sila equally spaced. So, we'll have to do some estimation na lang. So, this is 10 to the negative, let's just say na each marking dito, naka-linear na lang yung gagawin din natin. No? I mean, that is to say, linear yung exponents, I mean. So, kung negative 4 to, then negative 5 is somewhere dito. 10 to the negative 5. So, this is around 10 to the negative 4 point. And let's do an estimate. Let's do 10 to the negative 4.6 kunwari. Oh, kunwari ganyan. So, the ratio between PCO and CO2 is 10 to the negative 4.6. And if we evaluate that, let's use our calculators, no? And, wait lang. Yun, nakita mo naman ng calculator. So, we do 10 raised to the power of negative 4.6. That is 2.5 raised to the power of 10. Okay? So, 2.55. Sige. 2.512 times 10 raised to the power of negative 5. So, that is my final answer, no? Okay? So, if we were to find PCO and PCO2. And similarly, pwede din, and maybe you can do it on your own na lang, no? If gagamitin natin si H naman. So, kaya natin mahanap yung H2O ratio. Okay? So, obviously, pwede ding, if we go further pa, no, kunwari lang binigay yung PCO, kunwari lang sabi, we maintain the carbon monoxide pressure to ganitong value. So, if you know the ratio, then you just multiply or divide this value. You just divide the value with the ratio to give you PCO2, no? Parang ganyan. Okay? So, kung given naman yung PCO. And similarly, kung given din yung CO2, mahanap mo rin yung PCO kasi given, kumbaga nahanap mo na from the graph yung PCO2 ratio. Okay? So, I think that's it, no? Sa mga for the discussion of the Ellingham diagram. And let me just look at my notes, no? Kung meron pa ba akong na-miss. I think we're good, no? So that's Ellingham diagram. So I hope you learned how to use Ellingham diagram, and kumbaga sobrang na-simplify niya yung process, no? Sobrang kumonti yung calculations na involved. Okay? So, wait, meron pa pala ako idadagdag, no? Another feature of ano, no, and we can use this as an application sa ano natin for Ellingham diagrams is that if you look at it, yung Ellingham diagrams can also tell you kung ano yung parang ano, no, mas malaki yung reducing effect ng isang, or alin yung um, kumbaga magiging reductant if two systems are combined. Okay? So, if you, let's just say, ano, no, kunwari ito, hanap tayo ng mga nag-intersect. Mas madali kasi pagka nag-intersect. So, mm, let's look at this now. Si copper. Let's look at a system wherein meron tayong copper, tapos meron din tayong Fe3O4, no? So, if you look at it, this is the line for copper. Hello. Parang, wait lang. See, okay, okay na to. So, copper and Fe3O4, no? So, this is the reduction, itong line na to, this is the reduction line for Fe3O4, and this is the reduction line of copper, no? Oxidation, I mean. So, not reduction yung sinasabi ko. Oxidation, no? So, if I were to ask you, ano yung most likely mag-reduce if these two ano, no, species were in the same na parang system, no? If they were allowed to react. Okay? So, di ba ang sinasabi natin parati is the lower the delta G, the more spontaneous that reaction would be. Okay? So, if you look at, let's look at this temperature. Ito kasi, ito yung important part, no? Kasi ito, nag-intersect sila. So, if you look at that temperature, anong temperature? That's around 400, 600, 700. So, mga sa 600, sa 70, 650, mga 660 siguro. 660. Okay? So, itong point na to, this is 660 degrees Celsius. Okay? So, before 660 degrees Celsius, you'll notice na itong line na to, si Fe3O4 line, is below the copper line. So, what does that tell you? Ibig sabihin, more negative yung delta G value ng Fe3O4 plus O2. Tama? So, if more likely to occur to, kasi again, that's delta G, that's what delta G means, no? It is, kumbaga, the more likely, the more spontaneous reaction. So, kung more negative ka, you are more spontaneous, and therefore, you are likely favored by the system, no? So, ibig sabihin, eto, and if this were involved in a redox reaction, no, so one must be one must act as a reductant and one must act as an oxidant, no. Kumbaga, yung isa magre-reduce, yung isa mag-oxidize. So in this case, below 660 degrees Celsius, since this line is below Fe3O, then the oxidation of Fe3O4 to Fe2O3 must be more favored, no. And therefore, dapat yung sa taas, itong Cu should be reducing, no? So, kumbaga, ang more likely reaction to occur is the reduction of Cu2O into Cuo. Okay? So, ibig sabihin, si Fe3O4 acts as a reductant because it reduces, oh no, sorry, uh, acts as a reductant. Tapos si Cu2O acts as an oxidant for Fe3O4. Okay? Now, when you go past ano naman, 660 degrees Celsius, pare ito, past 660 degrees Celsius, notice na magkaiba na yung ano no, kumbaga iba na yung arrangement nila. This time, on top na si FE304 line, tapos nasa baba naman si copper line. So what this tells you is, beyond 660 degrees Celsius, the reaction, the oxidation reaction of copper is more favored than the oxidation reaction of Fe3O4, which means that beyond 660 degrees Celsius, it is more likely that your copper will be oxidized, and therefore it acts as a reductant for Fe2O3 to be oxidized into Fe3O4. So reverse reaction sa taas. Okay, so if they were in a redox system now. So in general, whenever you have a line that is below another line, ibig lang sabihin nun na yung nasa baba will be the reductant, tapos yung nasa taas will be the oxidant, no? So if you look at, tingin tayo ng malayo, no? Kunwari, zinc and titanium, they never, kumbaga, yung line ng zinc is always on top of the line of titanium and never sila nag-intersect. Therefore, at all temperature ranges, titanium will always oxidize and zinc will always reduce if they were in a redox system. No? So, titanium will always act as a reductant, tapos si titanium will always act as a reductant, tapos si zinc will always act as an oxidant. Okay? So, yun lang yung last na ano no, major parang application of this Ellingham diagram. So again, I hope you learned something new today, and hopefully magagamit niyo yung mga na discuss today on Ellingham diagrams to ano no, uh, simplify your calculations, as mas madali na dapat tayo makaka-solve ng mga delta G problems, and as well as yung mga PO2, as well as yung mga ratios din na yung pH2, PCO2 ratio na problems, no. Okay? So, yun lang, and thank you. Siguro I'll take this time to thank everyone for the wonderful sem, no, and hopefully I'll see you guys more in future subjects, no. So bye everyone.